everyone, and welcome to our group, Crystal Math. Today we are going to be modeling IED Blasts. Today's exercise is meant to explore the ways that differential equations can be applied to real-world problems. These problems can be small-scale, everyday things like filtering water or snails in a pond. Other times, it can be more explosive. Place yourself in the shoes of a military combat analyst. Your job is to protect your brave men and women from IEDs, improvised explosive devices. One of the detection RCs rolls over one of them unexpectedly and gets blown into the air.
What is an IED? An improvised explosive device, or an IED, is a very simple explosive device that have been used in terrorist attacks as well as roadside bombs against the military. Most IEDs only consist of a few simple parts, such as a power source, main charge, detonator, and a switch. To help further understand how IEDs work, we will be exploring the mathematical relationship of how an IED blast affects a victim. The top image shows an IED with a pressure plate used for roadside bombing, especially in Iraq and Iran. The second image shows Homeland Security's data on how much one should distance themselves from the corresponding amount of explosive capacity. How an IED works. The explosive is attached to a simple circuit where there's a switch that, when it is closed, completes the circuit, which allows the current to flow and activate the bomb, which is all attached to a voltage source. The circuit for an IED can be built by using a voltage source as simple as a 9-volt battery, a 3.6 ohm detonator, and a wire. Wire has a negligible resistance. Using Kirchhoff's voltage law, which states that voltage equals current times resistance, we are able to derive the equation for the current of the circuit. This lets us see how the circuit is complete. It is able to detonate the explosives. For an IED with a 9-volt source and a 3.6 ohm resistor, we are able to solve I equals V over R, where 9 volts is in the numerator and 3.6 ohms is in the denominator. I equals 2.5 ohms. This is only valid when the switch is closed. When the switch is open, there is no current. Here's Harris to explain more about the circuit.
So in this circuit, we have a battery which is attached to our load, which in this case, our load is an explosive, and along with a detonator on top. Now, all this is all coupled to a switch, and it's all dependent on this switch. Now, in the left, you see the switch is open. So when the switch is open, that means that current cannot flow and the explosion cannot occur. But as soon as we close this switch, which we can control at any time, current will flow and it will go into the detonator. And then from the detonator on, the explosion will occur. And more on switches, there are different types of switches where you have triggers, pressure plates, and other switches that could be used for different devices.
Here's a video to explain more about how IEDs work and the different type of IEDs that there are.
I'm Josh, I'm one of the bomb techs here at Tripwire, and we're just going to go over some of the items we have here, some of our inert training aids that we use for classes when students come through. First, we have just a real basic type switch used for improvised explosive devices, or IEDs. It's just a wooden and metal pressure plate. It's very popular in Iraq, Afghanistan, and also right now Syria. Power source that it functions with, as you can see, it's spring-loaded, basically functions as a switch. A person or a vehicle would travel over, closing these metal contacts, closing the switch, and then functioning whatever device it's hooked up to. And here we have a large explosive container. So something like this will be hooked to a switch like we just talked about. This doesn't look like much. It's a 5-gallon bucket with a handle. but a jug like this can hold 25, 30, 40, up to 50 pounds of explosive. Here we have a basic example of basically a suicide bomber vest that'd be worn around the chest. Devices like this are what was used in the Brussels airport attack, and this could contain a number of explosives or homemade or improvised explosives that can be easily manufactured out of a number of homemade chemicals or readily available materials at any department or home improvement store. Lastly, we have a pressure cooker type device, similar to the Boston Marathon bombing situation. The pressure cooker is ideal because it pressurizes the material that's inside and obviously allows it to build up and creates a more significant blast. Inside of this one particularly, we have fragmentation, just some nails. There could be anything from nuts, bolts, you could use coins, rocks, any sort of debris to cause more hate and discontent on your target.
And now we're going to be going into a quick introduction to first order or ordinary differential equations. Obviously this looks very complicated and very scary. However, this can actually be much more simpler than it actually seems. So if we were to look on this top model, where it says the standard form of a linear first order ODE, you basically have they all follow the same form, where you have the differential plus whatever function of y plus whatever function of x on the other side of the equal sign. And basically, using techniques, we could solve this to get a general solution. Now, this general solution is a function, usually a function of x or a function of t, or whatever function represented through another variable. And through this function, we could basically model things such as, the rate of an explosion, how far the trajectory of this explosion will be, many different factors and many different things within IED blasts. Now, you might notice and you might ask, oh, well, what is this integrating factor? This is just simply part of linear ordinary differential equations, where in terms of solving it, where you basically take where you take the integral to an exponential function of this middle term right here. And now we're going to turn to Craig for the application of the theory that is presented above for the first order ordinary differential equation.
Now it's time for the actual application of the math. Today's model will be dealing with a second order ODE. This means dealing with a second derivative to get our model. If we take our mass to be 100 kilograms, the drag coefficient to be 20 kilograms per millisecond, and the spring stiffness of the blast dampeners in the vehicle's seats to be 9 kilograms per millisecond squared, how could we model the displacement of a vehicle that hits an IED? The first step to getting our model equation is to start with simple physics. We start with an equation for the summation of vertical forces present at the moment of the blast. We can see in the equation below that the force of the blast pushes the vehicle upward, while gravity, drag, and the spring force from the seats dampens that force. You'll see that on the left side of the equation, since acceleration is the second derivative of position, it's notated with x prime prime. You'll also see that velocity, being multiplied by the drag coefficient, is just x prime. You might also notice that the value used for gravity looks a little different. That's because it's been converted to centimeters per millisecond squared. It's very important to keep your units consistent when doing your math. In this particular scenario, gravity's effect is actually very small, so we can ignore it for now. We can also divide out the 100 kilogram mass from both sides of the equation. After clearing out those terms and rearranging the remaining terms, we'll get x prime prime plus 0.2 x prime plus 0.09 x is equal to 1. Here we have a second-order non-homogeneous differential equation. The most straightforward way to solve an equation like this is by use of a characteristic equation. In this case, r squared plus 0.2r plus 0.09. By solving for the roots of this equation, you can form a general solution. Here you can see the steps we took to get our solution. We also solve for our unknown constants using our initial conditions. Since the vehicle is on the ground at the moment of the blast, x of 0 is 0. It also doesn't have any vertical velocity, so x prime of 0 is also 0. With that out of the way, we were able to get the equation you see at the bottom.
Another way we could have solved the IED blast is through a Laplace transformation, primarily when trying to solve the second order ODE by the use of the Laplace transformation. We reach a step after creating a partial fraction where it is a great challenge to find an inverse Laplace transformation, especially based on the material and techniques taught in class. Had we tried to use a Laplace transformation, the work for the inverse Laplace would have been too complex to solve for. The attempted work when trying to solve the second order ODE is shown in the next slide. As you can see, we could not solve for the solution because the techniques that were learned in class were not applicable here. So the equation that Craig just explained is represented in the graph as presented. The graph illustrates the displacement caused by the IED blast on a military vehicle. The graph shows that the vertical displacement of the vehicle after the bomb/IED goes off. Essentially, the graph is showing how the motion of the vehicle behaves. The downward curve represented in the graph indicates that the vehicle is moving toward the ground. The graph shows that the trajectory is moving in a positive direction even after the IED has hit the ground. This means that the position of the military vehicle is oscillating and bouncing between the air and the ground. As time passes, the IED will eventually be at a vertical displacement of 0 permanently.
Once you have a model equation for the displacement, you can take the derivatives of that equation to get models for the velocity and acceleration as well. The derivatives can admittedly get pretty bulky, so you might want to use a computer calculator. The ones we got are shown below. Here we have the displacement, velocity, and acceleration functions all graphed alongside of each other. Displacement is in red, velocity is purple, and acceleration is blue. You'll notice how quickly the acceleration caused by the bomb levels off to 0. This makes sense because, despite its lasting effects, the explosion is actually a pretty short event.
So a way to combat IED blasts is through blast-resistant seats. An IED blast can have enough force to take down a tank or other military vehicles. Knowing this, the military uses blast-resistance or attenuated seats. These seats are mounted onto spring systems with swinging footrests to assure that the least amount of damage is done to the passenger. Each seat has a harness around the body as well as head restraints to keep the passenger's body from jerking and moving against the motion of the chair. Here is a brief video to show how these seats work. The reason this works is because of the spring mechanism built into the chair. When a blast occurs and the acceleration of the vehicle and seats rapidly increase, the blast resistance seat is able to bring the passenger down effectively, lowering the acceleration that would be applied on the passenger. In the equation represented on the right in pink, we are able to see that the force magnitude is equal to the mass times the change of velocity over the change in time. This shows that the longer the period of time is, the less force that will be applied. The equation in the red shows that the spring constant, represented by the variable k, affects the time.
Oftentimes, there are many effects that can happen due to the blast of an IED. Exposure to these bombs have caused soldiers to develop PTSD symptoms. Those close to the explosion can have objects implanted into their skin. The blast can cause temporary hearing loss and burns on the skin. The most common injury is called blast lung injury, which can cause death and illness later in life. Some recent terrorist attacks that IEDs were used in are the Oklahoma City bombing, and that IED is commonly used in mining and blasting. The 2005 London bombing, that IED did not really have any common uses, but instead used materials from other different types of IEDs. The 1993 World Trade Center bombing, which that IED is commonly used in fertilizer, and the Olympic Park bombing, which that IED is normally used as ammunition. All of these attacks were done by using different types of IEDs and also by using a combination of multiple IEDs in one.
So the question is, what should you do if you encounter an IED? If you are near an IED, the first thing you should obviously do is try to get as far as you possibly can from that IED. However, this is not always possible or the case, so here are some ways to protect yourself depending on where you are. If you're inside a building and if objects are already falling, get under a desk or table to seek cover. If it is clear to leave, exit the building and use the stairs. If you are outside a building, stay away from any hazardous materials such as windows and glass doors. If you are moving after the IED was set off, cover your mouth and nose so smoke and dirt do not enter your system. Alert any safety officers using signals or lights. Once again, try not to scream or panic, because you can inhale dirt and other dangerous toxins. In conclusion, IED are simple explosive devices that hold many uses. There are mathematical relationships as to how an IED blast affects a victim. Differential equations can be used to model different scenarios concerning the people involved, the many different events that can occur, as well as the many factors that come with IEDs. We are able to limit the damage done by IEDs by using the current blast-resistant building and seat technology.
How do you think that the military should adapt the designs of the blast-resistant seats and their tanks to prevent future fatalities due to IEDs? What should be implemented into big buildings and busy locations to reduce the effect of an IED? How can the blast-resistant technology be implemented into everyday cars?